Okay. So since the time allotted for this particular training is limited, so I'll be covering each some analysis from each and every package. These are the 3 packages provided by the SolidWorks simulation. So there's a standard package, there's a professional, and there's a premium package. So in case of standard, you get the basic analysis. They may be static analysis where loads are not a function of time. So loads won't vary with respect to time domain. So you can perform the fatigue analysis, in which you can find out the life and durability of your component. I'll just bear with me for some time. I'll come to these terms. This may be new to you guys, but just bear with me for some time. I'll explain each and everything in detail. So in the professional package, you get to see the frequency as well as the thermal. These 2 domains we will be covering in tomorrow's session. And finally, in the premium package, we will be covering the nonlinear static. So these 3 to 4 types of analysis I'll be covering, and also I'll cover the motion analysis that is there in tomorrow's session. So basically, moving forward.
Sorry to interrupt, Sujay. Sorry to interrupt.
Yes, sir. Yes.
Considering the education module, so if NIT Durgapur down the line, any organization, those who opt for education packages, so the entire simulation package, whatever they have shown, Mr. Sujay had shown in last slide, simulation standard, professional, premium. So every education institute got the complete gamut of SolidWorks simulation capabilities. So it is not categorized in standard, professional, premium when it comes to education. So every module will be covered in the SolidWorks education packages.
Okay.
Please continue.
Yes. No, sir. I just I was showing that what kind of analysis I'll be covering, since the time is limited. Absolutely. So I want to show the maximum things, and which will be useful for the students in the coming future as well. That is why.
Please.
Okay. So when I say that we are going to perform the first static analysis, so why we perform the static analysis is, if we have multiple design configurations with us or multiple design alternatives with us, we want to check which of the design are going to be feasible for the manufacturing or for production or for usage in the real time. So we can apply different types of materials on those design, consider different types of structural condition, that is change the shape and size of those designs, and check if it is going to be safe under the static loading condition. That is, the loads are going to be static. The load is not going to change with respect to time. So there's no impact loads are considered, or some rapid generating loads are not considered. We are considering the stationary loads. So for the best example is that the chair on which you are sitting, it is the static load that you are applying on the chair. Moving forward, we will be covering the frequency analysis. I'll show you some glimpse in today's till the end of the day session. Tomorrow we'll cover this topic in detail. So why we use the frequency? To find out the different mode shapes. So when we cover the frequency analysis, I'll show you that what exactly are the mode shapes, what kind of results are we getting out of it. And this particularly is used for the noise and vibration reduction things, or whenever your operating frequency, you must have, I'm sure that you must have learned about the concept of resonance. So if your operating frequency matches with the resonating frequency or the natural frequency of the structure, there's a chance of failure. So how we can avoid that? By adding certain material or changing the stiffness of the component, that we can find out with the help of frequency analysis. So this is one more topic that we'll be covering, that is the thermal analysis. So thermal in this particular domain deals with the heat transfer. I think since all of you are in the second year, so the heat transfer is yet to come to you, but you are familiar. I hope that you are familiar with the basics of the temperature distribution and how it affects your stresses. That is, if you increase the temperature of on certain metal component, it may undergo some kind of expansion, and we can learn those things in this particular domain. Also, we can perform the various material comparisons with the help of this thermal analysis. So this is the nonlinear analysis. We'll be seeing this in tomorrow's session. So basically, nonlinear deals with the scenarios where your your strength is going beyond the yield point. So what exactly happens is when the strength or the stresses in the model go beyond the yield point, there is a possibility of permanent deformation, or we call it as the plastic deformation. So in order to check the deformations in that particular zone, how certain materials are behaving when they cross the yield point, we can see this with the help of nonlinear analysis. I'll show you why we perform particularly the nonlinear analysis. What is the exactly the difference between nonlinear as for and linear static analysis, how the loads are applied. I'll be showing that to you. Also, we can see the permanent deformation that is occurring in your model with the help of nonlinear analysis. So moving on forward. So whenever in case of the industries, if we consider, there are multiple moving components there. So they are always in the vibrational state. So due to those particular vibrations, there might be a possibility of development of stresses or deformations on your assembly or on your part. So in order to find what kind of effect they are causing on your assemblies, that we can find out through the dynamic analysis. So fatigue deals with the SN curve data. So in your design of machines that you are yet to learn, you'll learn about the SN curve. In this particular domain, we won't be covering the fatigue analysis, but I'll show you. I'm just telling you that it deals with the life of your component. So whatever in the market you see that the certain component has this kind of warranty or this kind of guarantee, that has been calculated with the help of fatigue analysis. So it gives you the life estimate of your components. So there's optimization. This is the special dedicated advanced tool available in the SolidWorks simulation. It basically deals with the removal of material without compromising with any kind of stresses or without compromising with your safety factors of your component. Then this is the special domain that is available in the SolidWorks simulation portfolio, pressure vessel design. So in industry, if you go to the particular boiler industry or steam generation industry, they have a ASME code of conduct that they need to follow. So those whatever the procedure is there that needs to be followed in that particular code, this pressure vessel design, this domain is based on that only. So whatever the criteria of them are there, so those criteria are followed and you get the values accordingly, and you to test your models. So finally, there's a drop test. So this is the virtual dropping of material from certain height. So suppose you are dropping your mobile phone that you are using from certain height. So what happens in the industry when they are manufacturing the mobile phones, or they are designing the mobile phones, they perform this particular test in order to capture when the mobile hits the ground, how it hits the ground, what edge is going to be contact with the ground first, and how due to the impact the crack initiation may happen. So this kind of features or this kind of data is collected with the help of this particular drop test. So we call it as the explicit dynamics. So it's a bit advanced topic for this particular training domain. For the sake of your just knowledge, you can note it down that this particularly comes under the explicit dynamics. So whenever certain impacts are happening, during the time of those particular impacts, suppose a crash analysis is happening. So when a vehicle is crashed into a certain restraint or certain pole, so during that particular crash timing, what exactly are the changes happening in the body? Those are calculated with the help of explicit dynamics. So this was a basic overview of all the products that are available in the SolidWorks simulation. Now we'll move to the FEA part of it. So what exactly is finite element analysis? So suppose I want to get the groceries from the nearest store. So, and at the same time, since I'm having the engineering mind, I want to measure the distance from my home to the nearest grocery shop. So how you can measure it? There's a one way that I also have the measuring tape with me. So after I'll break down the overall path in the small number of instances, which will be equal to the distance of my measuring tape. So this is how, since by breaking down into small number of instances, I can find out the total distance that is there from my home to the nearest grocery shop. So this is how the FEA process is followed. So what we do is we break down the overall assembly into small number of parts, and on those particular parts the calculations happen in the backhand, that is using some numerical methods, and then it is extrapolated to the overall assembly, and that is how we get the results. So when I move to the SolidWorks simulation window, you will come to know about the process exactly, what exactly happens. I'll show you that. So prior to building an FEA model, there are certain steps that needs to be followed. So there's first is the CAD geometry. Then there's a simplification of geometry. So as a FEA engineer, it is your duty to remove unrequired faces or unrequired features from the geometry. So in this particular case, you can see that it is having certain fillets at those edges. So for the simplification process, what I'll do, since these fillets are of not my importance to me, I'll remove those particular fillets. I'll consider the edges. The purpose of doing this is that on those particular fillet area, there's a possibility that elements will be very smaller. So I'll explain you the relation between smaller elements and the solving time in a bit when we move to the SolidWorks window. Just go through, I'll just walk you through this basic procedure that needs to be followed. Then after simplification of geometry, we import it into the FEA. So where we perform the type of, we select the type of analysis. So in the previous slides, I have explained you what different types of analysis are there. Then we apply the material to it. Different material properties are there. So accordingly, we apply the material. We apply the supports and loads. So this is what the boundary conditions that are there that we can define in terms of FEA. So suppose and if you are having the basic knowledge of strength of materials or mechanics, you must understand, or you will come to understanding that the reaction that are happening in the model, accordingly based on that knowledge, you can apply it here and apply the boundary conditions to the model. So in order to fix your geometry in space, you can apply the supports. In order to find the results, you apply the loads. Then we follow the process called discretization or meshing. So we divide this complete model into small number of parts. Those are known as elements. And then we send it to the numerical solver and see the results. If the results are according to our need, we will finalize the results. If the results are not according to our need, we'll then make certain design changes and again follow these steps and again solve it. So this is the basic workflow of building an FEA model. So what exactly FEA stands for? There are different terminologies that are involved. So mesh, nodes, and elements. So I'll quickly go through a window. I'll explain you what exactly are these things. So, okay. So now we will be talking about the single element. What exactly is this? So in terms of SolidWorks, I'll show you just a second. Quickly draw. Okay, so this is the single tetrahedral element as we call it. So it is having 4 points at the edges, at the end of the edges. So it is having 4 sides, that is tetra, and 1 vertex. So that is why it is called a tetrahedral. These are the 4 edges points where it is connected to. So when I move to this particular slide, you can see that the whole bracket, this bracket, has been divided into small number of parts. So I have just drawn the single part out of this. So combination of these parts forms this particular bracket. So why this is necessary? That in order to calculate the results, the SolidWorks doesn't understand the CAD data, right? So it needs to capture the geometry that is involved. So what I'll do, I'll first create the CAD data, then I'll import it to SolidWorks, where SolidWorks simulation. So where it will convert this data into the meshing geometry, which it understands for the formulations. So it will divide it into small number of parts called as the elements. Those elements are to be connected with each other, called as the nodes. So the points that I have shown. So the 4 points, 1, 2, 3, 4. These are the 4 points that are forming. So this is the single element. This element will be connected to other element at these nodes. So whatever the displacement formulations are going to form, so after application of load, what kind of deformations we are getting, we will get those at this particular node location. The calculations, the solver will calculate this in the backhand at this particular node locations. And this particular thing is known as element. So this is the single linear that is draft quality element, tetrahedral element, you can call it as. So there are different elements which we use for the different types of geometry. So whenever I want to capture a 3D geometry, like an engine block, which is having certain length, certain breadth, and certain height, so all 3 dimensions are of significant, at that time I'll go for the 3D or solid elements. So we call it them as the solid elements. So since the deformations are calculated at the node location, solid elements are quite stiffer as compared to the shell elements. So what exactly is the shell? So if this is my single element, whenever I am dealing with the sheet metal components, which is having certain length, certain breadth, but the thickness of the sheet metal component or the along the cross section is constant, at that time I can use the shell elements. So when we see this analysis performing in detail, you'll come to know, or you'll understand it in much better way. I'm just telling you how the shape is of this particular elements is there. So there are certain differential equations that are partial differential equations are calculated when the solver is solving this or formulating these particular elements. So from the data from these particular elements is considered for solving the differential equations in the backhand. So in this particular training session, we won't be covering the backhand, what processes are carried out in the backhand. We will be simply covering the aspects related to the SolidWorks simulation, which will be easier for you to understand. In your final year, maybe there's a subject called a finite element analysis, where you can learn the processes that are involved during the backhand operations in detail. So these are the 2 types of element that I've just shown. There's a one more, that is the beam elements, and how it affects your geometry, that we'll cover when we cover that particular topic. Okay, so is this idea about the elements and nodes is clear to all of you? Simply type yes in the chat box so that I can understand that you are getting. Can you all type in the yes? Okay. Okay, I think all of you have understood the concept of elements and nodes, so we'll move forward. So just remember in short that elements combine to form the complete body, and this formulations or this solving process or the finite element analysis, the analysis is performed on these particular small elements, and then these small elements, the data from the small elements is extrapolated to the whole assembly or whole part, and we get the results at the end. Okay. So there are three types of elements that are available in SolidWorks simulation. So there's a solid, there's a shell, and there's a beam element. So I've shown you the solid tetrahedral element in the SolidWorks window here. So this is how the one solid elements looks like. So basically, since it is stiffer, when if I apply a load to a single element, it won't deform as it is. So the each and every element, or each and every node, or each and every object in space has almost 6 degrees of freedom, right? 3 translational, 3 rotational. So in terms of solid element, they are having only 3 translational degrees of freedom, since the elements are quite stiffer. So if I apply a load on this particular element, so a single part of the element, it will move in the x, y, z direction. If I apply a load, it won't be able to rotate. That is, if I'm fixing this and apply a load, we won't be able to see deformation. So I'm showing you the help of this. So if I apply load, this won't deform like this, since it is stiffer in size. So as you can see the curvature that I have drawn on this particular element, so it won't deform like this. It will simply be stiffer, and whatever the changes we can observe, those will be in terms of the translation. So after the application of load, it may translate in x, it may translate in y, it may translate in z. But for example, you can consider for 3D or solid elements, you can consider the example of suppose a duster. So if you try to bend it with your hand, you won't be able to bend it, but if you slide it on a certain plane, it may translate in that particular plane. Or if you throw it from certain height, it may change the height location. But if you try to bend it with your hand, bare hands, it won't be able to bend. So that is how one example you can follow to understand this concept. So whenever I talk about the shell elements, so as I've told that whenever we are dealing with the sheet metal components which are having uniform thickness throughout its length or throughout its bed, that is the cross section is uniform, you can consider the shell elements for those particular examples. So I think you must have learned about the sheet metal in the previous training session. So if you perform any kind of sheet metal operations and you make the geometry here with the help of sheet metals, you get as an output when you import it into SolidWorks simulation, you get directly the shell mesh on it. So after performing the meshing, you'll get the shell mesh. So when we move to the SolidWorks simulation window, I'll show you this and you'll be able to understand it in a better way. So what happens in terms of the shell? So you can consider the mobile cover as a shell element. So if I want to bend the mobile cover, it may bend if I with my bare hands, right? So what exactly happens is shell elements or the beam element, that is the structural members which are having only significant length, the thickness, the cross section is throughout is the same. So I'm talking about these two types of elements here. So one is the shell elements which we apply to the sheet metal parts. The solid elements we apply to the geometries which are having significant length, breadth, and height dimensions. And whenever we are dealing with the structural members having the uniform cross section, we consider the beam elements. So why we consider that we'll learn in some time. Just understand the concept before. So what happens when I am trying to bend this particular, if you can imagine this particular sheet metal component, if I want to bend it with my bare hands, I can be able to bend it as the shell elements have 6 degrees of freedom. Okay. So if I'm considering this particular problem, if I want to bend it, it can translate in the XYZ direction. So there's no doubt about it. since it is free to move in space. Now, when I try to bend it and apply load from certain heights or press it with my fingers, with my thumbs, I can be able to bend it in this particular y direction. So the shell elements have 6 degrees of freedom. That is, it can move in the translational direction along the x, y, and z axis. Also, if I want, I can also rotate it. If you consider this as the z axis, and I see in this direction, I can rotate it in z direction. I can also rotate it in the x direction, or if I want, I can rotate it in the y direction. So if I fix certain points on this particular location and I apply certain load, this may deform in this particular direction. So the one more example, as I've already told, is the example of the mobile cover. So you can bend the mobile cover according to your needs, where if you want, and it may deform, that is, the bending moment is observed in the mobile cover, and also it can move in the planar translational directions. And then comes the beam element. So whenever we are introducing the weldments feature, yeah. So whenever we are drawing certain structural members with the help of weldments feature, those will be directly converted into beam elements. So the beam elements is simple to understand. Consider the top plane. So it is having only, it will look like this. So there will be 2 nodes at the end and 1 element in between. So since my structural members is going to have a uniform cross-sectional area throughout its length, due to which we can consider the beam elements, the section properties will be considered in the back end of the problem, and those won't be displayed to us on the screen. So during the numerical calculations, it will consider the sectional properties that it has derived from the section or from the area or from the cross section, but we won't be able to see it. Why this happens is, since you can see here, the 3D this solid elements or tetrahedral element is 3D in shape. So what it requires is, it requires more graphical memory to process this particular structure. Why? Because it is having 3 degrees of freedom, that those are the translational. So the solver needs to, in order to capture the geometry in proper detail, more of these number of elements are created. So I'll show you once we move to the SolidWorks. Just bear with me till then. Did you guys understand the concepts of shell, solid, and beam elements? I'll explain you where exactly are we going to use them, but did you understand what exactly I was trying to say here, related to degrees of freedom? If you understood that, simply type yes in the chat box so that I can know that you are getting it.
Can you repeat the beam element once again?
Okay. So what happens whenever we are dealing with the structural member? So suppose a I-beam is there, or C-section is there, or a certain circular rod is there. So if you observe all these elements, they are having the uniform cross-sectional area throughout the length. Okay. So for these particular cross-sectional members which are having the uniform cross-sectional area throughout the length, so I'll just draw one thing here in order to understand in a better way. I'll simply draw a circular rod. So this may be of certain length, not worried about the length at that time, at this time. So this is, if this is the particular structural member that I'm going to use in my assembly. So you can observe that it is having the significant amount of length, but the thickness is constant throughout the length. The thickness is not varying. So if I consider an engine block and I compare it with an I-beam, so engine block is having particular dimensions in all the 3 directions. So it is having certain dimensions, certain value of dimension X, Y, and Z direction. But if you consider this particular beam elements or structural member, it is having the length as the significant dimension in the Y direction only. It is not having much of the significant, or the value of the cross-sectional area or the thickness of this particular pipe is quite small as compared to the whole length. Okay. So what happens is when we consider the beam elements, which whenever our assembly consists of uniform parts, at that parts having uniform cross sections throughout the length, we convert them to beam elements. Or if we are considering certain structural members, like we are involving I beams, C sections, or pipe like this one, at that time the software will convert, or I can tell the software to convert these into beam elements, which will save the meshing time. So your meshing time is meshing size is directly proportional to time for solving. So more the number of elements involved in your model, more the degrees of freedom there will be there to solve. Accordingly, the model will take much more time to solve. So when I'm considering this particular beam elements, it will have only two nodes at the end, as shown in okay, the figure we failed. Okay, I didn't save it, but I have drawn a single line. So when I import it into SolidWorks simulation, it will simply be shown like a single line and two nodes at the end. It won't consider the 3D geometrical or graphical interfaces of this particular shape. So in the backhand, the solver will consider all the sectional properties that are involved. It may be the moment of inertia involved in this model, or if we simply go to evaluate and check the section properties of this particular thing, we calculate. Just a second. Okay, I want to select the section. So whatever the sectional properties that are involved, so you can see here principal moment of inertia, moment of inertia of the area, that particular area in the L, X, Y, and Z direction, whatever is involved there, the software will consider these values in the backhand. It won't show you the graphical representation of this. So when we cover the last last topic in today's session, there's a involvement of all three meshes in the single assembly. And at that time, you'll come to understand these things better, how this is graphically represented. So the only thing is that, only thing you can understand from here is that solid elements, which capture the geometry more properly, they create more number of degrees of freedom. Shell elements, since we are not considering a thickness, the thickness will be considered in the backhand of the software. We are, for the graphical representation purpose, it will be like this, single sheet metal of no thickness. So for that, the elements that are to be created along the thickness will be omitted here, but the thickness properties will be considered in the backhand. And this also beam elements, that cross-sectional properties will be considered on the backhand. For graphical purpose point of view, we will only be able to see a single line with two nodes at the end. So is it clear?
Yes, sir.
Okay. So we'll move forward now. So this is how they are represented. Here you can see it is a tetrahedral element that I have shown. So there are two types of tetra elements or shell elements we can use. One, there's a draft quality. So whenever the software will develop the linear differential equation, I hope you must have learned about the differential equations. So when the power of the differential equation is 1, at that time, it will create this kind of tetrahedral element. When I increase the power of the differential equation, it may be 2, 3, 4, or any polynomial power. There are certain nodes that are introduced in between the two nodes. So if we move to this particular thing, okay. So you can see the 4 nodes that I have drawn on this particular tetrahedral element. So this is having the power of linear. This we can consider as the linear differential equation. So in the background, it will solve the linear differential equation. So whatever the deformations are occurring, those are always occur at the node locations. So and the data from these node locations is considered for the solving purpose. So what when I turn it to the higher quality element, that is I increase the power of the differential equation, the solver will introduce more nodes in between. Okay, so in total now there are 10 nodes introduced in this particular element. So what happens whenever I apply a load? I told you that the deformations occur at the node locations. So since it gets one more additional mid node in between this, now it will try to deform more accurately after the loading condition that is applied on it. So earlier what was happening, only the 4 node location that at the vertices, those were deforming and it was capturing the data for the calculation purpose. Now it gets more nodes, mid nodes for calculation purpose. So it will try to capture more deformations related to this particular element. So more data is captured in this process. So this is how you can define the high quality or parabolic mesh element. So this comes with the tetrahedral. Similarly, when we are dealing with the shell elements, it will have 3 nodes at the vertices. When I increase the order of the elements, the mid nodes are created here. So now you can see earlier it was only deforming at these 3 particular locations. After introduction of 3 more nodes, it is more easily deformable. So why we use this particular concept in FEA, that there are certain small fillets involved in my geometry that I need to capture more properly. So if I introduce more number of elements, more of the geometry will be captured in my analysis, and the closer to the actual results, I may get the results closer to the actual values. So the more number of elements you introduce, your results are going to be more accurate. But at the same time, since your degrees of freedom are increasing, your solver time may increase drastically. Okay. Just type in yes if you are getting what I'm saying here, what kind of relation that I have just explained. Hello. Okay. Got it. So I assume that you have understood this thing that I have tried to explain to you. What exactly is the element? What are the solid elements, shell elements, and beam elements? What in these 3 particular types? What are the subgroups? So there's a linear or draft quality elements. Then there's a parabolic or high quality element. So when we increase the order of the elements, when we change it from linear to parabolic, it will capture the more of the geometry, more the small features that are involved. It may be curvatures, small fillets that are there, and we can calculate more accurate results. So FEA is totally based on the numerical methods. So the first assumptions of the numerical methods is you don't get the actual results, you get the results closer to the actual values. So there might be certain truncation errors and all those errors that are involved in defining the element, defining the results. So it is saying that, or it is the fact that whatever actual results you get, those you get at the on field, on site, where the actual loading and different types of vibrational or actual loading conditions are occurring. So why we use FEA, since we are not getting the actual result, but the purpose of FEA is to get the values closer to the actual values that are happening. So if you introduce more number of elements in your model or in your geometry, you will get more closer to the actual value. Yes. So one thing you can, yeah, but when you move to the industry, if you are working as a design engineer, by his point of view or his view, if you are designing certain component which is having the yield strength of, let's say, 250 MPa, and your design requirement is that your stresses may not go beyond this particular value, yield strength. So I'll apply certain factor of safety to it after solving, and if I'm getting the values close to the 150 MPa in the actual FEA analysis, I'm getting my result of the stresses as the 150 MPa or 170 MPa or 175 MPa. So at that time, or even if we increase the loading conditions and I'm getting the values close to the 210, 215 MPa. So even though these particular values are close to the yield strength, so there's a chance of the failure. So no designer in the world will design a component which will have stress values close to such a yield point or a tensile point. So this will give you an idea about how you can design better prior to manufacturing. So it may happen that you have designed certain bracket, you are applying the mild steel to it, so the yield strength is almost 350 MPa, and you are testing it. You are not performing any kind of FE on it, so directly you are sending it for the manufacturing. So what happens when it comes to the manufacturing phase, and after applying the loading and after operating for some time, it fails? So the designer who has not used the FEA prior to the manufacturing, he can't tell why exactly is this failing, right? So he has not considered any kind of loadings prior to designing his bracket, and he has just without validating his results, he has sent it for the manufacturing. So this is completely wrong approach. So in the process, you are costing the company valuable time as well as the money. So in order to avoid all this hassle, it is always recommended after designing your component, you should validate them with the help of FEA. Then again, if you find the results are according to your requirement, you should send it for the prototyping, and then it is sent for the final manufacturing if you are considering the mass production. If you omit the step of the analyzing with FEA, it may be harmful for your organization where you will be working. Okay, so whenever we know that if we consider a coordinate system or any kind of element that is in space, and we apply, we basically consider the von Mises failure criteria for performing the FE analysis, that is the shear strain energy criteria. So according to this particular von Mises criteria, if we apply a loading on certain components, it has three normal stresses and three shear stresses. So this is the formula for von Mises. If you want, you can write it down for your reference. While going through SolidWorks simulation, we won't be reading this formula, but if you want for your knowledge, you can write it down. So Sx, Sy, and Sz, these are the normal stresses that are involved in a model. So you can normal as in it is perpendicular to the plane. Whatever the component you are considering, those stresses are perpendicular to the plane, and we consider them as the normal stresses. And tau x, txy or tau xy are the tau is the shear stresses that are involved in your model. So whenever you are applying certain kind of loading conditions, your component may experience these kind of stresses. If shear stress component is not there, we can say that only principal stresses are acting, that is only the normal stresses are acting. And then there's a factor of safety. So basically whatever the value you are getting in actual to the maximum, if we find the ratio, we get the factor of safety. This is the basic behind finding the factor of safety. So in our case, since we will be first covering the static analysis, the maximum value will be the yield strength value, and limiting stress will be the whatever the value we are getting as the stress value in our as an output in our model. So now I'll talk about the linear static analysis. So this is the first and very basic analysis that we will be covering today. So what exactly is the linear? So you must have learned in your strength of materials also that your elongations is the equal to FL by AE, right? So it is elongation is equal to F, that is force, times length divided by cross-sectional area into Young's modulus. So the first assumption is that linear static analysis is they are elastic in nature. So if I apply a load, it won't pass the component or the just a second. Yeah, the component won't pass the yield point, and whatever the as soon as I remove my load, it will regain its original shape. That is what elastic means. One more assumption is that if I apply a load of, let's say, 100 Newton, I'm getting a displacement of 2 mm. If I increase the load to 200 Newton, obviously due to the first assumption and the behavior, we will get the displacement as 4 mm. So since we apply the increase the load accordingly linearly, the deformations may vary. This is the one of the assumptions. The second is materials are linearly elastic in nature. So as soon as I remove the load, it will regain its original shape. So if I consider the stress strain curve also, just a second. So this will be my stress. Sigma. This will be my strain. So we will consider the stress strain curve for the steel material. So first, this is the elastic zone. Then beyond this point, the component enters the plastic zone. This is the yield point. Then there's some deformation that is occurring, permanent deformation. And finally, you may get the stress strain curve like this. So at this point, this will be your tensile strength, tau T max. This will be your yield strength. So whatever the material is experiencing stress or strain in the elastic zone, we will be covering this particular zone in terms of the static analysis. So this, we are interested in this particular zone. So in this particular zone, Hooke's law is obeyed. So whatever the load I'm applying, the component will deform or will behave in the certain manner. As soon as I remove the load, it will again regain its original shape. So this is what one of the assumptions of the linear static analysis. And the final assumption is that loads are static in nature. So in the beginning, I have given you the example that if you are sitting on your chair, or if you consider certain mobile tower, due to the self weight of the mobile tower, it is only going to experience that particular that particular weight throughout its lifespan. So these types of loadings are known as static loading. So the loads is not going to be vary with time. Loads is going to be stationary for whatever the time duration that we are considering. So these three are the basic assumptions of the linear static analysis. So linear as in the material is linear in behavior. So after the removal of load, it will regain its original shape. The material elastic in nature, it won't enter the plastic zone, and the loads are static in nature. These three are the assumptions of the linear static analysis. So I will walk you through the basics analysis process. Okay. What about the lunch? I was told that we need to take a lunch break. So just type in the should we take a lunch break for half an hour and come back later, or should we cover this? Just type in your answers in the chat box. So accordingly, we'll proceed. Hello? Hello, am I audible?
Yes, sir. Yes, sir.
Yes, so I was telling that since it's almost 2 p.m., what is the time exactly? So we'll take a break, lunch break for half an hour. We'll come back later. It's almost 1:43. So 1:45 to 2:15, we'll take a lunch break for half an hour. Is it okay with all of you? Yes, sir. Okay. So we'll take lunch break from now till 2:15, and then we'll cover the rest of the procedure that is involved. And after that, we'll take a tea break around 4 and try to cover as much as possible today. What was the timing that I mentioned? It's around. Okay, so we'll cover today most of the topics that are involved here. So see you guys in half an hour.
Okay, sir.
Yeah. Yeah, am I audible now clearly?
It's okay.
Okay, students. So everything till now we have covered some basic aspects related to the FEA. So I hope those things are clear to you. So we have seen what exactly is the mesh, what exactly are the elements, what are the nodes, then what are the different types of elements. They may be. Let's just simply go there. So different types of elements. There may be solid shells and beams. What are the subtypes of those elements and how they affect your simulation results? So there may be linear, that is the draft quality elements, and the parabolic or high quality elements. And then there's a shell elements which we particularly use for the sheet metal components. Then in case of shell, there's a draft quality, that is the linear, as well as the high quality, that is the parabolic elements. So simply we are introducing some mid nodes into the element in order to capture more geometrical deformations properly. And then there's a beam element. So in case of beam elements, the cross-sectional properties will be considered in the backhand for formulations. And the graphical representation will be like this, as you can see on screen. So you can see, just a second. So you can see the graphical representation of these particular types of elements when we apply on the geometry, how they will look. This is simply for the purpose of graphical representation. All the properties will be considered in the backhand. So you need to remember this. So we saw the three basic assumptions that are followed in case of linear static analysis. So the responses are proportional to the applied loads. The loads, the material is linearly elastic, and the loads are static. Okay, so I'll just walk you through the basic analysis process that we follow while solving the simulations. I'll introduce you to the FEA simulation window for the first time now. So in this particular example, we'll be seeing the introduction to the simulation interface, different material properties, what kind of material properties are important while solving the linear static analysis. Then defining the boundary condition, that is the restraints and the loads, then meshing, and finally we will run the analysis, and how the density of the mesh affects your result, that also we'll see. So we will quickly move to the window now. Just a second. Okay, starting then with new part. This is my CAD window. I'll quickly draw a plate with hole. So keep it as 100 mm. Let's keep it at 200. Draw a hole in between. So this is 50. Extrude by 10. So my plate is complete now. I can also apply a material from here, from the material library, or I can apply it in the simulation window also. So in order to start the simulation, the process we will follow, please pay attention to the process. It's actually simpler to understand. There's nothing much difficult here. So click on simulation in the simulation tab. If it is not available, click on tabs and you can start it from here. The simulation tab, there's a new study. So these are the different types of analysis types that are available that I have already told you about. So first we will go through the static analysis, and then so now I am into the SolidWorks simulation window. You can see here new static one study has been created. You can name the study whatever you want while creating the study itself, or you can rename it from now. So I'll say plate with hole. So the first step while performing the analysis is to simplify the geometry. Since in this particular geometry there are no unnecessary fillets or chamfers or unnecessary holes, so geometry simplification is not required in this case. So we'll directly apply the material. I can apply the material from the material library that is available with SolidWorks. Okay. So as you can see here, as soon as I open the material library, there are different materials that are available here. Whether it may be steel, iron, aluminum, you all must be knowing this. So the new thing here is when I click on any of the material from the list, it highlights certain properties here in the red color. So that means for performing this particular static analysis, I need to have these properties with me. So if I'm selecting the material from the material library, these properties are going to be there. If I create a new material in the material library, so I need to enter these particular properties which are highlighted in red color for the completion of analysis. So in this particular case, for the static analysis, if I'm not considering any kind of thermal effects in it, so suppose the thermal expansion or thermal stresses, I'll be selecting the I'll be needing Young's modulus, Poisson ratio, and density. So you need to have these three properties. Yield strength is required for the purpose of calculating the factor of safety. Then moving forward, if you want to check the destruction level of the material of the component, you should have these properties with you. Thermal expansion coefficient is required when we apply the temperature loads in your model. So if I am applying a temperature to this particular plate with hole, so this plate, and due to the temperature rise, how it will expand, or due to the temperature change in temperature, that is cooling, how it will contract, that effect is calculated with this thermal expansion coefficient. So you all must be knowing this, but you need to have this value with you. So for this static analysis, we need to have these four values. So since I'll select alloy steel, so values are there. Simply click on apply. The material has been applied to the geometry. As you can see here, earlier the tick was not there. So this tick indicates that material has been applied, and you can see the material here as well. So connections we'll be seeing in the when we will perform the analysis on the assembly. Since this is a single part, connections need not be given here. So the next thing is to apply the boundary condition. So I want to simulate it for the tensile load. So I'll fixing it from one end and applying the tensile load on the other lane. So this is a simple problem to just make you understand the procedure that we follow. We will see more advanced problems related to assembly.
Sir?
In the yes.
Sir, will you please again show how you got the chart of the strength and ratios?
Sorry.
I mean, just a minute before you showed the chart where the tensile strength or Poisson's ratio were there.
Asking a chart from the
Okay,
material.
Got it. So if you right click on the part that you have, when you import, you start the simulation. I'll again, no issue. We will create the study again. So go to new study. Here I'll select the static as the my analysis type. This is the another part that we'll cover maybe tomorrow. Use 2D simplification, how you can use it to reduce the geometrical shape or meshing time. So I'll name it as the plate with hole. I hope all of you have SolidWorks installed on your laptop or computer, whatever you are using for this particular training session.
Yes, sir.
Is it there? Okay, yeah, no issue there. So you don't just solve simultaneously with me. I'll give you some time after explaining the steps, and then you start at your own end. This particular study is only for the purpose of understanding the steps. You need not solve this. If you want, I'll give you some time after the this study ends, and you can solve it at your end. So now you can see this particular symbol. You can see here. It is a solid geometry. So this particular indicates the type of element that you have applied. You can apply the shell element to this also, that we will cover in the next topic. But for the time being, this indicates that this is a solid geometry. That is, if I mesh this, tetrahedral elements are going to be created. Simply right click here and go to apply/edit material. So material library will be opened. From this material library, you can see that the properties that are highlighted in red, those are the necessary properties that we need to have while solving this particular type of simulation. So if we are going for the let's say nonlinear analysis, the properties, some additional properties may be here which are required for solving nonlinear analysis. Or if we are solving thermal analysis, so specific, it would highlight the specific heat in red color. So this is how it changes. So depending on the type of analysis you are selecting, you need to the software will tell you what properties are required for solving that particular analysis. So I'll select as all the properties are there.
Sir, is this chart fixed or we can change it according to our requirement?
No, you can also change it if you are applying different materials. So suppose you are working in a company and you, at your end you have received a material test certificate of alloy steel which are having different properties. So simply you can create a new material out of this. Copy this. Go down here. Here you will find custom material. Those are created by the user, that is me. So you can see create here. New library. You can directly create material here, or can enter new category, whatever the category. So alloy steel created by, or I can maybe 101. Let's say. I'll say paste. So the material is pasted here. So now you can make whatever changes you want. So if I want the Young's modulus to be 220 GPa, it's not 210. So I'll change this value. I want the Poisson ratio to be around 0.3. 0.3. Shear modulus, since it is not highlighted, it indicates that it is not required for performing static analysis. So I may not change it. If I want the mass density to be 7800 kg per meter cube. So accordingly, you can make the changes. If I from the material test certificate, you get the data as Poisson's ratio and yield strength. So if in your particular material test certificate you are having this value as different, you can enter. Let's say it's 550. So you can apply this value here. Also, you get to choose the linear elastic or isotropic material or linear elastic orthotropic. So when I select isotropic, that means all my material properties, it may be Young's modulus or.
So what is isotropic and orthotropic?
Yes, that is what I am explaining. Yes. So when I click on isotropic, that means my material property, whether it may be Young's modulus, it is constant in all directions. Okay. So for this particular plate, if I am applying the isotropic as the condition, so along its I just want to see the triad. Yeah. So along X direction, along Y direction, and along Z direction, the material properties are constant. Those are not changing with respect to directions. When I select orthotropic here, so the elastic modulus and Poisson's ratio, those are varying with respect to the particular direction. So in X direction, the Young's modulus may be different. In Y, it may be different. In Z, it may be different. Similarly, Poisson's ratio. So this is the main difference between isotropic and orthotropic materials. So I simply
Sir, when orthotropic, sir, I can understand the case of orthotropic. Please once explain, please.
Okay. So whatever the material properties that are defined here, suppose you are dealing with certain laminates in your structure, or your component is having it is made up of let's say, okay. So your component is made up of different types of materials. So accordingly, based on the properties of the different materials, these particular properties, that is, it may be Young's modulus or Poisson's ratio, they are going to change in particular direction. So when we are considering isotropic, so throughout this component or a plate, the properties are going to be constant. So in any direction you move, you will find Young's modulus value as 220 GPa. But if I change to orthotropic, it says that Young's modulus in X, Young's modulus in Y, Young's modulus in Z. So you can define the values accordingly. So whatever the loading you are applying, the structure may behave that in that case. Just sorry. Yeah. Okay, I forgot to apply it. So let's just create it again so that you can understand. Okay, here from here also. So here you can see when I'm applying the orthotropic as my property, and if suppose this is on this plate, I'm applying a tensile load on this end, so it will try to elongate in X direction. Also, I'm applying a tensile load or compressive load on Z direction. So if I'm considering the property as isotropic, the behavior that I'll get, it will behave that considering the Young's modulus as 220 or 210, whatever I have provided it or whatever is there. But when I consider the orthotropic, the behavior due to the Young's modulus, due to this tensile loading will be different, and due to this compressive loading, if I apply a compressive load on this plate, it will be different. So basically, we calculate elongation in any component as FL by AE. I have in the earlier session, I have told you that force times length divided by cross-sectional area into Young's modulus. So your elongation is inversely proportional to Young's modulus, right? So in whatever direction you are applying the load, if you are considering the orthotropic material, the elongation will be dependent due to this particular load based on the Young's modulus value that you are feeding to it. Understood? Or is there confusion?
Yes, sir, I understood. Yes, sir, I understood.
Okay. So we have considered isotropic for this particular example. Now apply the fixtures. So SolidWorks allows you to apply different types of fixtures according to your need. There's a fixed geometry. So what this will do is, currently, since I have not applied any boundary condition, that is the fixtures to this, it is free to move in space. So if I apply a load, it will show me that there is some error. It is not fixed in space. You need to first fix this and get the results accordingly. Because in case of strength of materials also, when we find out the stresses or deformation, we get those stress values at the restraining point, right? Suppose we are solving the simple examples of, let's say, cantilever beam. So if I am considering the cantilever beam, the maximum stress value or the maximum stress value I'll be getting at the fixed end where it is fixed with a wall. So this is how it works. You need to first fix this in space. So to do that, we have fixtures. There are different types of fixtures available. So fixed geometry will fix this in space. So it won't allow it to move in X, Y, or Z direction. At the same time, it won't allow it to rotate in X, Y, and Z direction. Then there's a roller or slider fixture. So if I want to imitate the movement of a roller or a slider, so suppose I'm applying a load, let's say 10. First I'll apply the load, that will be easier to understand. Okay, so I'll apply tensile load, let's say 1500 newtons. So due to this tensile load, now it is free to move in space. If I fix it from here, it will only elongate. If I allow it to, let's say, roll on a surface. So consider it is placed on a surface and I'm pulling it from this side in the X direction. So on that particular surface, it will start rolling. So to imitate those kinds of fixture, we use roller slider fixture. Suppose this bracket is rotating at this particular circular hole. So there's a shaft coming from here along Z direction, and this is rotating along it. But I want to simulate only this particular plate. So in that case, I won't be considering the shaft for analysis, as it may increase my solving time due to the additional meshing requirement. So for that particular type, I'll use fixed hinge condition. So it will behave like a hinge that we see on our doors also. Then there's an elastic support. So if I want the fixture that I'm applying it to be having some stiffness, so at that time I can use elastic support. If I choose fixed geometry, it will have infinite stiffness. Then there's a bearing fixture. So similar to the hinge fixed hinge condition, if the shaft is rotating in this particular hole, I can consider this. Then there's a foundation mold that we'll be covering in the next topic in detail. We will be using foundation mold at that time. Additionally, there are some advanced fixture available here. So instead, I want it to move. Let's say I don't want this face to move in X direction, but I want it to move in a YZ plane. So here you can see it can be moved in the YZ plane, but I don't want it to move in the X direction. So I don't want it to move forward. At that time, I can select from the advanced fixture. I'll select this one. So there are 3 options available. The first is along plane direction one. That means if I consider this plane, so it will restrict the motion in Z. If I consider start this along plane direction 2, it will constrict the motion in Y. And if I allow it to move in normal to plane, so it will from here I can decide for how much distance it can translate in X direction. So if I enter here, say 5 mm. So after the application of load, okay, it is telling me to tell a reference point. So when I simulate it, due to this load, this plate will be moved to 5 mm distance, but it won't go beyond that. This is the use of this particular fixture. If I keep it as 0, so in X direction, it won't move at all. So I'll consider fixed geometry at this particular end and click on OK. Okay, so fixture is applied. Then moving on to the forces. So there are different forces that you can apply. That may force, torque, pressure. So if your force per unit area is there, you can apply the pressure. If you want to calculate the self weight of the component, so since we have applied the density to this via material property, you can consider to find the self weight use applying the gravity condition. If it is a rotating part, I can apply the centrifugal from here and apply the centrifugal force and find out due to the rotation what kind of stresses are developing. Similarly, you can apply the bearing load from the shaft, or if there's some bearing in between here. And if you want to see the temperature thermal stresses or thermal deformations, that is what kind of expansion or contraction that is happening due to the change in temperature, you can apply the temperature here. And then there's a flow effect and thermal effect. These are some advanced topics. So in short, I'll tell you that there are 2 more modules available in case of simulation. So there's a flow simulation that deals with the computational fluid dynamics, and then there's a thermal simulation that we'll be covering tomorrow. So in case of thermal simulation, we deal with the heat transfer related to the component, and from those heat transfer effects we can include in our static analysis to find out the stresses and deformation that are developing due to the thermal heat transfer problems. So those are quite advanced features available here, and we will not be covering these 2 things. Then also prescribed displacement. So if I want this plate to move in space, I can apply the prescribed displacement. So I'll simply allow it to move by certain distance. Then the remote load and remote mass we'll be covering in the next session, so you need not worry about this right now. Okay, so our boundary conditions are done now. You have defined the fixture and applied the load, so it is fixed in space. Then we will be creating mesh. So I need not be going into detail related to the course and find that we'll cover in the next topic and how it impacts your simulations. I'll simply saying okay. So this is how now the solver has captured the geometry. It has divided, after capturing, it has divided into small number of elements, and now the formulations are going to happen on this element. Okay, then okay. So our basic procedure is done now. The next thing is to run it. You can run by right clicking on the topic from here, or you can select run this study from here also. So it has, okay, you might have missed the window. Just a second. We will rerun it so that you can see what exactly happened here. I'll simply change some value of force.
So what is this?
Yeah, I'm telling you just. Okay. So this is what these are your results due to the application of this loading condition, how your structure is behaving. So originally it is set to a deformation scale of 2944. That means the results or the graphical representation of the results is exaggerated. This is only for the sake of understanding how the trend is happening in the model. You simply need to scale it to 1:1 to get the true results. So now it is deformation scale is set to 1, and now it is telling me that maximum stresses. So you can see from the legend on the right side, this is the legend. Your yield strength is 620 MPa, and your maximum 1 measure stress is going up to 22.063, and which is coming near this portion, these two locations. And as we move away from it, you can see that color is changing to slightly blue, which indicates the stress is reducing in this particular area, and high stress concentration is observed at this particular two locations. Okay, so this was about the stress plot. Then there's a displacement plot. You can see here again the deformation scale is set to this value. Click on true scale. So the purpose of deformation, so it is showing me a maximum value of 0.007. So this is how much it is deforming due to the load of 5000 tensile, 5000 in tension, and maximum deformation is occurring at this particular side. As you can see, it is in red, and since we have fixed this, minimum deformation is happening in this area. So this is about the basic procedure that we follow while performing the simulations. Now we'll move to some advanced things. So in case of mesh, I'll go to create mesh. So it is asking me that since earlier I have applied the mesh to this body, should I, if I make any changes to mesh, the result that I have gotten from this will be changed also. So I'm saying okay, and the things are there. So there's a coarse and there's a fine. So if I create it coarse, it is increasing the element size, global element size. So the size in the earlier session, I have told you that how a tetrahedral elements looks like. So this will define the side or edge of the tetrahedral element. And here you can select whether you want to go for the high quality and draft quality. So in case of high quality, I have explained to you that we introduce more number of nodes, mid nodes are introduced, which will allow it to deform in a better way. But at the same time, it will be computationally expensive. So first, we'll keep it at coarse. Let's change it to draft quality for the first. Then we'll go see the results for high quality. Click on OK. You can see here, mesh is colored in orange color. Also, since we have considered the draft quality, you can see how, since the elements are having only 4 nodes at their ends, the one we saw in the tetrahedral element that I've shown you, that is why it is not able to capture the circle more properly. So you can see there are edges formed here. So in order to capture this particular surface or for a particular round shape or curvature in this area, I have two options. I can either decrease the size of these elements. So if I decrease, more number of elements will be created and the geometrical shape of the circle will be captured more properly. Or I can increase the power of the element. So there are two options available. In the first one, since we have selected draft quality, it is not able to capture the this particular circular curvature properly. So now we'll see the results. You can see that since earlier we were getting the value of 22, now it is only 13.105. So stress value has been decreased drastically. The reason for this is the solver is not able to capture the geometry properly. That is why it is providing less number of elements for calculation, and which is resulting in inaccurate results. So in order to capture the geometry properly or get the accurate result, you need to have a smaller number of smaller size of elements, which will automatically increase the number of elements. So if I go here, mesh, and select details, so you get all the details related to your mesh that you have applied. So we are considering element size as 11.303, tolerance as this one. So this tolerance indicates that when the element will try to capture the curvatures, till what value should they capture the curvature value. So I'm telling that whatever may be the circular area, circular diameter here, you capture the whatever may be the circular diameter here, you capture it up to 0.56 mm of its diametrical value. Then it has created total number of 434 nodes and total elements as 1332. Aspect ratio and okay, I'll explain these things also to you. So aspect ratio is basically a quality check that we follow in order to make sure how I mean, whenever we are simulating, we are getting results, but in order to finalize on the results, we follow the quality checks. So if the element quality is good, that means the results are going we can trustworthy, we can say. So if the element quality is bad, that is determined from the aspect ratio. So it is the ratio of maximum element size to the minimum element size. Just a second. Okay, I'll quickly create a shell element. So if I have created an element like this, so if this is 218.59, this is 82.72. So aspect ratio will be the ratio of these two lengths. In ideally, this aspect ratio should be 1. That is, all the sides should be equal. But while meshing, the solver will mesh it according to its needs. So we may not be able to capture these parameters always, but we need to make sure that we are getting close to the value of 1 as the aspect ratio. If I say equal, so if I want to create a shell element or shell mesh, the aspect ratio size should be equal. So the ratio of maximum to minimum should be 1. This is what the aspect ratio means. So when I move here, plate with hole, see the mesh result detailed. So you can see it is telling me maximum aspect ratio is 3.4. So there is some element which is having maximum size or maximum edge length to minimum edge length in the ratio of 3.4. That is what it means. Yeah. So it will also tell you percentage of elements with aspect ratio less than 3. So it should be close to 95 to 99. So it's 99.5. So if we get the results out of this, we can conclude that yeah, since the aspect ratio or the element quality is good, we can finalize the results. And if this ratio is greater than 3, so aspect ratio greater than 10 is like 3%, 3 to 5%, so or greater than 3%. So we should remesh the model with smaller element size. So now I'll change the mesh again, mesh quality. Now we'll just consider the just okay. I want to note down few things. Okay. So total number of nodes here are 432. elements 1332. Now we'll apply a high quality mesh here. So create mesh, yes. Mesh quality, again shifted to high quality now. Okay, it has remeshed it. Now you can see the color has been changed, and the curvature, earlier you would see the curvature was not properly captured, but since we are using high quality elements, they have mid nodes in between them. So earlier I have told you that what are the mid nodes and how they are defined in case of high quality. So that is why the curvature is more properly captured at this time. And we'll see the number of elements created now. So total nodes, high quality, it's okay. High quality, in case of high quality, total nodes are created 2558. Earlier it was only 432. So more mid nodes are created, keeping the number of elements as it is, 1332. So between these elements, since I have told you that draft quality element, or when we chose the draft quality element, it has one tetrahedral element has only 4 nodes that I have shown in the beginning. Do you all recall that? Simply reply in chat.
Yes, sir.
Okay. Yeah. And when we change to high quality, the 6 additional mid nodes were introduced, due to which this number has been increased drastically. So that is how it affects. So when we introduce more nodes, your solving time will be increased. So earlier the solving time was just a second. Can I see that? Solver messages. So total solution time was like 0 seconds. It solved immediately. Let's see if this value changes now due to the addition of number of nodes. I'll click run. Okay, it's telling 0 seconds. Since the geometry is not very complex, now we will increase the number of elements involved in the model. Let's see if it has any effect on solving time. I'll create fine, so it will create more smaller elements. Now you can see it is taking some time to solve, and how small elements it has created. So you can see the curvature of the hole is more properly captured this time. Now if I run this, it will take some time, more time to solve this. Earlier you didn't see this window as it was solving very quickly. Now it is taking some time and going through different simulation steps. Now, solver messages. You can see it took almost 5 seconds to solve it. So this is how your simulation results effect depending on the type of mesh and for what duration, what size, element size, for what quality you are applying to it. Depending on those factors, your simulation results will vary. Obviously, if you apply smaller element, that is finer mesh to your model, you'll get better results out of it and closer to the actual values. So I hope the basic procedure to follow while performing FEA is you understood this thing. Just simply type yes in the chat. If someone has any problem related to this, I'll tell that thing again. Okay. Are you guys having SolidWorks right now with you?
Yes, sir.
Okay, so can you try one problem at your end just to make sure that you have understood the procedure?
Yes, sir.
Yes,
Okay.
sir.
Okay, I'll tell you that simply draw in CAD, draw let's say I-beam of 100 by 80 by 100 and having thickness of the eye as, okay, I'll help that. Okay, just draw this section that I'm drawing on my screen at your end and apply a load of, let's say, 10,000 Newton to it. So first I'll draw it. It as, let's say, 10. So simply, okay, just one thing, this machine here. This must be 140. Okay, let's make it. Okay. So draw simply I-beam of this cross section. This value we will keep as 140. Okay. All of you are getting the dimensions at your end. Keep this 10. This also 10. Okay. So I hope all the dimensions are clear to you. Okay. Draw this I-beam and apply the length as close to, let's say, 500, extruded by 500 mm. Can someone of you present his screen so that I'll know at what point you guys are? Can someone share the screen with me? Whom should I say?
Sir, what should be extruded thickness?
You extruded by 500 mm.
Okay.
Okay, that's good. Now, as I've shown in the this session, apply a fixture on one side and apply a load of, let's say, 1000 newtons. Make it compressive load. Don't apply the tensile load. follow the steps that I have followed during the presentation.
Sir, how have you added that simulation tool?
Okay, yeah. So in SolidWorks add-ins, there's a button SolidWorks Simulation here. If you click on that, it will add one more tab here as simulation. So you need to click on this, go to new study and create your study. Understood?
Sir, the simulation is not available in that tab.
Okay. In SolidWorks add-ins, is it there? SolidWorks Simulation?
No, sir.
Okay. Just go to add-ins. You must see a gear-like structure known as options. All of you are facing this problem, or someone else? Some of you are facing this problem.
Sir, now I have added that. So will it be pinned for always, or again means if I
Yes. No. It depends. In add-ins, whether you have
checked that.
the startup, you have checked it. If it is checked, so if it is active add-in,
Yes, sir.
if you click on startup, it will be on always.
Okay. Sir, how much force should we apply on
Apply
the
load of 1000 newtons. Apply compressive load. Don't apply tensile load as I applied it. Apply compressive load.
Sir, please repeat how to add simulation. It
Yes,
is not
sure.
showing.
Okay. In the SolidWorks add-ins, can you see SolidWorks add-ins there? The tab is there.
Yes, sir.
Okay. In that, you can see a button called SolidWorks Simulation. If you click on it, it will add here a simulation tab. If the tab is not there.
Okay, sir.
Did you get it?
Yes, sir.
Okay. Everyone is done with the setup?
Sir, only we have to do, we have to fix one face and apply the force, right?
Yes.
Anything else?
No. Just this exercise is just to make you understand that what kind of steps are there while performing the simulation. There's nothing much in this. Okay, I can see your screen. Just a second. Yeah, great. So I applied the yes. So applied the compressive load. It's not visible to me. Yes. Okay, no issue. Yes. Got it. You can solve it. Okay, I'll be back in just a couple of minutes. Done, everyone? Okay, so after the class, you can also try it with different mesh quality. Try it on from your strength of material book. If you are having certain problems related to beams, you can try them or validate them with the help of FEA. So I think according to me, this way it will be more easy to understand the behavior if you apply the loads or if you do it practically in FEA. It's just my opinion. Okay. Okay, so one more thing is to compare the analytical and the FEA results. So since the load and the dimensions, I did not follow those things. If I would have created the plate with these dimensions, I would have gotten this value. Then this is simply the analytical formula. This is the force per unit area. This is the area on which we will be applying the load. So cross-sectional area is there. W is the width of the plate. D is the diameter of the hole. And T is the thickness. So we will get the cross-sectional area out of it. And sigma N is the normal stress that we'll be getting with the help of analytical formula. And this is some factor that if we multiply it by this factor, we'll get this value, 409. If we would have considered the dimensions they provided related to this particular problem. Since I have created the plate with my dimensions, the results or the stress value may be different in my case, or individually in your case also, if you have created the plate or whatever the I-beam, according to your dimensions, the stress values are going to be different. So this is just to compare what kind of results we will be getting. And to conclude out of this is that, so which results to follow, whether I should go with the analytic or whether I should go with the FEA results. So I'll tell you a small difference between these two things. In case of analytical results, we can calculate this with the help of certain empirical formulas. We can find out the stresses and deformations in linear structures, or which are not very tedious to understand the structures. But when the structural geometry is very complex, at those times the application of analytical methods is bit tedious to work out on, as it may take a larger time. I'm not saying that we can't calculate with the help of analytical methods on complex structure, but it is a quite time consuming process. So compared to that, if we move to the FEA, we may get results closer to this value. I'm not saying that we will get exactly these results. We will get results close to these values. So in the earlier session also, I have told that which thing to consider or while finalizing. So the actual thing is that when you are making the prototype and it is undergoing the loading conditions at on site, you will get the actual result. So suppose on site I am getting the stress value as 350. So FEA will tell you that while you perform the FEA analysis, the stress values may come around 320, or they may come around 310, or they may come around 340. So the close to the actual results you will get with the help of FEA. So I'm again repeating that the FEA won't give you accurate results. They may give you the approximate to the actual value. So no software in the world can give you this result, because all the softwares are formulated based on the numerical methods, which formulate based on the approximations, and they don't give you the actual values. Okay. Yeah. So the next thing we will be considering is the context while we will be simulating an assembly. So this is a small example of a Cardan joint. We will be learning multiple things in this assembly. Just a second. Okay. So I've shared this file with you of the Cardan joint. Just for understand what procedure I am following during this process, and I'll give you some time after that to solve it at your end, so that it will be better to understand. So this is basically U joint. This red blob will be applying certain load, and we'll be seeing how the structure is behaving. In this lesson also we will be learning the concept of contacts. So till now we have only simulated single parts. So when the assembly is introduced in simulation, you need to tell the software what kind of interactions are happening between the respective parts, so that software can understand how to apply the movement to those particular parts in order to capture the geometrical or stress results or deformation results more properly. So this is one thing that we'll be learning. Then we saw mesh refinement, but in this particular case also we'll learn about the mesh refinement. Also in the previous lesson I've told you about that there is a concept called remote load and remote mass that I'll be showing in the next session. So that also I'll be explaining. And connectors. There are multiple things that we need to understand in this particular lesson. Okay. You can note these things down, X, Y, and Z locations. In your notebook, simply write this down. X, I'll explain you what these things are when I'm solving it. Just for your data purpose, write these things down. X equal to 57.15, Y equal to 24.16, and Z equal to 0. So just write this down. And force in Z direction minus 2.5. I'll explain you what these things are in a minute. So are you guys done? Have you written the values of X, Y, and Z?
Yes, sir. Yes, sir.
Okay, great. Okay, so we'll move to SolidWorks simulation window now, and while solving or while doing it, I'll explain you what things are there in this particular analysis. So I've already shared the file with you. There are two files. One is the unsolved one, and there's a solved one. So for your reference, I have given the solved one also. I'll start with the unsolved one. In the completed folder, there's a solved file, and if you select this assembly, it's unsolved one. So for your reference, you can refer the completed file. Open. So this is the basically cardan joint assembly. So my purpose is to rotate this lever in along y axis, and to see the results or the motion transmit from here to here with the help of this bracket. So this bracket will be the holding factor. Also, we'll learn the concept of connectors in this particular analysis. So you can see there's a hardware involved here. There's a nuts and bolts. Also, there's this pin. So for the sake of simplification, as I can model these things in SolidWorks simulation, I need not consider this while making the CAD, which is to be imported into SolidWorks simulation. So I have created another configuration with it without crank, and we'll see how the things pan out here from here on. So when I use the connectors or from the toolbox, SolidWorks toolbox, I have the opportunity to convert these connectors into SolidWorks simulation connectors directly. So what this will do is, since this CAD model will be converted into SolidWorks simulation connector, the meshing that is to be done on this particular CAD model will be reduced drastically. So it won't consider this model for meshing, but it will consider how it is keeping these two parts fixed together. So that is how it will help us. That is where the connectors come in play. So just I'll show you what exactly happens. So whenever I'm involving the connectors from the SolidWorks Toolbox library, you can see this one more option available, that is convert toolbox fasteners to bolt connectors. So what it will do, if I click on tick here, let's say first we will mesh it with the coarse one. Click on OK. So you can see here the connectors are gone from here. 4 simulation bolt connectors were successfully created. The software understood that these are the simulation connectors which are joining two bodies. So this bracket and this bracket is connected by the two boards. So in the connections now, since we are dealing with the assembly, there's a new folder here which tells us about the different connectors that are involved. So SolidWorks has created the CAD data of these connectors into the simulation connector. This is only possible when you are importing the tools hardware from the SolidWorks Toolbox library. If you have created bolt on your end, that is, you have made the CAD model out of it, and you are then trying to import it, then it won't happen. It will only understand when you have created or considered the bolt connectors from the SolidWorks Toolbox library. So now it has created bolt connector, that is the data of the connectors which is joining these two plates has been considered now. So you need not model this. So what this has done, that as you can see here, or the bolt connectors are not there, bolt and nut are not there. So the solving or the meshing required for these particular bodies, I need not mesh them now, because the solver has considered them in the backhand at its end, and it has created the connector on its own. Okay, so there are different types of connectors like this. So this one was the bolt connector. There's a spring connector also. So the purpose of connectors is you need not model the CAD model on your part. You simply consider the properties of it so that your meshing time will be reduced very drastically. Sorry for that. Okay, so there's one more connector, that is the pin connector. There's bolt that we are using now. You can define the bolt connector additionally from here also. Right click on it. There are different bolt connectors available. The standard counter bore, countersunk, standard, counterbore with screws, countersunk with screws, and accordingly you need to select the faces where we want to define the connectors. You can also select the connection type. So if I consider distributed, that means the connector or the bolt that I am defining, it may undergo certain deformations or it may have certain stiffness of its. So whatever the force will be transferred through the geometry, it will consider the stiffness of those bolt connectors and it will transfer the force accordingly. If I consider rigid, then the stiffness will be infinite and the bolt connector won't go any kind of deformation. Then you can consider the material that you want to apply your bolt connector. Similarly, it is connected to the material library. So any material you can select from there also. Or you can create the custom material depending on it. You can define the properties of it. Then you can define the strength data. So here one thing to consider is tensile stress area and calculated tensile stress area. So if I consider known tensile stress area, I need to define the tensile stress area. So where my bolt connector is going to be fixed, in whatever hole, I need to consider the area of that particular hole while adding this value. So if I want to apply the connector or bolt here, I'll consider the tensile stress area and go to evaluate, go to measure, select this. So it is giving me an area of 69.461. So I'll enter that value here. And it will, while simulating, it will consider this area for the further calculation. So calculated, there's a known tensile stress area and calculated tensile stress area. So if you know the pitch of the bolt, you can consider the reciprocal of that. So threads per mm is the reciprocal of pitch. Pitch is basically the distance between the two threads. So if you can imagine any bolt, you can the distance between any two threads on the bolt is known as the pitch. So reciprocal of that is thread per mm. You can enter this value here. Then you can also apply the preload. So while using the bolts in assemblies, also in the real life, we apply certain extra load in order to make sure that the bolts are stuck tightly and they may not move when the machine and start vibrating or moving. So in order to make sure that they are stuck together or they don't fly away while the working of the machine, we apply the preload. So the basic is that when I'm tightening any bolt, it okay. How? Just a second. Okay, I'll try to explain it to you here. So suppose these are two surfaces on which pardon my drawing, it's just too difficult to draw on paint. Okay, so suppose this is my bolt that is fixed into two. This is one surface and this is another surface, and this is nut. Okay, so what I can do is this may be hole. The hole may be having some internal threads. Suppose like in this area or in this area. So these may be the internal threads that are there. So what exactly happens is when we are tightening any kind of bolt. Just a second. Yes. So when I'm tightening the bolt, what happens is if I'm applying the load from the top, suppose I'm tightening it in this way, in the clockwise direction. So at that time, the nut will try to move upwards. But since this is the surface, that will restrict the nut, but the bolt is rotating, so the threads will try to apply force on the nut, which will, but since the nut is unable to move upwards, the threads or the shank inside the nut area will try to expand. So this particular phenomena is known as bolt tensioning. So whatever the load is applied during this particular process is known as bolt preload. The purpose of doing this is to tighten the bolt accordingly so that it won't fly off during the operations. So we apply always, while tightening, we apply some additional torque or additional load to the bolt assembly wherever we are fixing it. So this is what the concept of bolt tightening comes in. So that if you are using the spanners, different spanners have their torque ratios defined. So based on that, you can define the torque value, what kind of torque you are applying, or axial force as a pre-tensioning force that you are applying. So this particular data you can insert from here. Also, in case of as I've told you about the bolt, there are different connectors involved. So if you want to simulate or check the weld spots in your assembly, if you are joining two sheet metal components with the help of welds, so you can apply the spot welds connector. Then you can consider the edge weld connectors if you are applying the butt weld. Then if your connector component is having certain link between them, the two, and you need to consider the, if one component moves, depending on it, the other components move. So at that time, you can apply the link, or you can apply the rigid connection, so that whatever the interaction between the components, it will pass through the rigid connection. So the whatever the connection we are defined, it won't deform according to the force transfer. So these are the different types of connectors that are used during the process. In this particular scenario, we'll be going with the bolt connectors only, since the bolts, as I've already told you, bolts were imported from the simulation toolbox, SolidWorks toolbox. They are directly converted into bolt connector, and we need not define anything extra. Okay, so the next thing is assembly. So there are now, since I have imported the assembly in SolidWorks CAD, what happens, we apply certain types of mates. So you can consider the concept of connector or contacts similar, analogous to mates only. But whatever mates we define in SolidWorks CAD, those are not imported into SolidWorks simulation. We need to define connectors to tell the software how the components are behaving with respect to each other. So suppose there's some kind of sliding motion involved in your model between two components. So we need to tell the software that these two components are sliding on each other, and you make or you consider those factors while simulating. So there are local contacts, other component contact, top level component contact. So I'll explain you what exactly is this. So top level component contacts is known as global contact, and local contact is the contact that we define between the individual components. So there are two basically contacts that we use mostly, that is the bonded and the no penetration. So for that purpose, I will walk you through one example which will be easier for you to understand. Okay, I'll consider a top plane here. So there we will be learning about the bonded as well as the no penetration contact at this point. I'll tell you with the help of an example what exactly are these two types of contacts. Toolbox. Okay. So I need to have these two as different bodies. So I'm unselecting merge results. So I'll get two solid bodies differently. I'll quickly go to SolidWorks add-ins, simulation, new study, static, apply a basic material, let's say plain carbon steel. Now, since there are multiple bodies, more than one body is in here, that is, this is multiple bodies are involved. So it has created this global bonded contact between them. So what this means is that these two components are stuck together now. When I choose bonded, that means they are glued together. This is the meaning of it. So if I select bonded here, there are two options: allow penetration, bonded, and no penetration. We hardly use allow penetration. We mostly use bonded and no penetration contact. Compatible and incompatible, I'll tell you just wait for one. So globally it is selected bonded contact. I'll quickly apply fixture and let's say apply a load, or we will apply displacement this time. So I'll apply prescribed displacement on this face. I want this as the reference. I don't want any movement in upward direction, no movement in longitudinal direction, but I want it to move by a certain, let's say 10 mm. Create a mesh and run this. Okay, sure. Okay, so as you can see here, the behavior, since I have applied the bonded contact, since it is stuck to the or glued to the model, bonded contact does this. It glues the two components together. So when I am trying to move it by certain value in the x direction, since it is glued together, it is unable to move forward. So it is deformation scale is set to 0.5. We'll click on true scale and maybe we won't be able. Okay. So you can see it is not the proper behavior. Even though it is not the proper behavior, the purpose of this is to make you understand the difference between bonded and no penetration contact. So you can see here it is taking the area on which it was glued to the bottom plate. It is dragging it forward. So this was about the bonded contact. So when I change to no penetration contact, it will incorporate what I can say sliding motion on this too. So if I say no penetration here, I can, when I'm choosing the no penetration, I can introduce the friction coefficient here, which will define the stresses that are contact stresses that are developing between two components. So I'll say frictionless since for now. Click on OK. Okay. So whenever I'm introducing, okay, so now you can see when I move the bonded contact, if I displace it now, it is going forward now. I can animate this. So now when I use the no penetration contact, you can basically introduce the sliding motion between two components. With the help of, if you want, you can also define the friction coefficient. But if you introduce bonded contact, they will be glued together and they won't be able to move. So where we exactly use this is when I want to, let's say, simulate two components which are welded together. So at that time, I'll go for the bonded contact. If from the customer or from the on-site, I know that by seeing the operation that the two components are going to move with respect to each other, there's going to be relative motion or there's going to be sliding motion among the two components. At that time, I'll go for the no penetration contact. Okay, clear these two things, bonded and no penetration contact. Simply say yes in chat so that I know that you have understood.
Yes, sir.
Okay. So I think most of you have understood this, so we can move forward. Okay, so this was about global bonded and local, global bonded and no penetration contacts. Global means whatever the assembly components are there, to the top level assembly, it will apply that type of contact. So if there are more than, let's say, 5 components involved, if I select bonded, if those components are in contact with each other, they'll be glued together. If I consider no penetration, all the components will be glued together. But if I right click here, there's one more option, that is contact set. So this will allow you to define contact between the two components individually. So even though I apply a bonded contact to the whole assembly, let's say we will consider bonded contact, or I'll introduce one more module for your understanding. Okay. So now there are 3 bodies. If I keep this global contact as the bonded, so each and every body will be glued together now. But I want, for example, there are a number of bodies, and I want few bodies to be bonded, and I want few bodies to move with respect to each other. So there is no possibility to define 2 contacts in this place. So what you can do is go to connection, define contact. So now I will define a local contact, that is, even though it has been bonded together, now I'll tell it that he remove the bonded contact first and apply this new penetration contact, as I want to incorporate this one. So to do that, select this phase. In what phases you are defining the contact, you need to select those phases. So the bottom face of this block and the top face of this block, I'm considering them that they will have relative motion, but this block will be fixed together. I am not applying any kind of friction, as the friction formulation is computationally expensive and it will take more time to solve. Then since it is connected by surface to surface, as you can see here, the bottom surface and the top surface, it's better to define it by surface to surface contact. If you are simulating certain like a gear train, so in gear train you won't have surface to surface contact. Your gears will move with the help of line contact, right? So in that case you should go for node to surface or node to node. Any one of you can use. And click OK. So now I define a load to this. Okay. Okay, let's try this now. We will try to move 2 faces at the time. Okay, okay. When you can apply the load on single body also, single body only at one time. So to define the loads on this, I need to define one more condition. You can apply the displacement, or you can apply the load. Anything you can apply. Okay. Okay. So now what will happen? This will, since global bonded contact is applied, this will try to stick. Since we have not defined any kind of contact between these two, it will be stuck together, but this will try to move. Okay. So this is how global and local contacts work. So you need to remember that local contact will always override the global contact. So whatever the global contact you have defined for your assembly, if you define the local contact, it will be overridden at that particular location. So let's come back to our, I'll quickly animate this. Okay, it is moving, it is not moving. So I hope that you all understood the concept of global and local contacts and bonded and no penetration contact. If you have doubt related to this, please ask. I'll explain it again. If not, we can move further. Simply type in chat that you have understood. Otherwise, we'll move forward.
Sir, once again, local contact.
Yeah, okay. So what happened in the previous assembly that we have applied the global contact to the whole assembly. There were 3 parts involved, right? So what global contact does, we have defined the global bonded contact. So what that does, whatever the components are in contact with each other, it will try to glue them together, bond them together. So if I define global contact, all the components will behave like a single part, for example. But when I define the local low penetration contact to the smaller block, it allowed it to move slightly, but we have not defined any contact to the bigger block. That is why it has considered the global contact that was predefined and glued it to the bottom plate. Okay. Shall I okay, understood, or shall I move to that problem again? The problem with 2 blocks?
Yes, sir. Problem
Understood.
with 2.
Okay.
No, sir.
Just a second. Sorry, yeah. I shouldn't have deleted it. I quickly draw 3 blocks here. Both are almost same in G. Just a second. Okay. So now I have 3 blocks involved in my model, right? So I'm going to Solidworks Simulation. You can see here 3 solid bodies. When I merge them, it will be single body and it will behave as a single part. So you need to have different bodies to apply the local contacts. So now component contact, it is set to the global bonded now. So we will try to move this now. Fix this. Let's say move it by 10 mm in the X direction only. We will define one more. You move that direction. Let's say by 5 mm, not in any other direction. This is what I am telling it. You only move in X direction by 5 mm, not in YZ by any movement. Okay, these 2 things are defined. So when I run it, it will, okay, material is not defined. You can see here 3 bodies are created, material is not defined. Again, carbon steel. So when without meshing, directly click on run, it will first mesh on its own by the default mesh and try to solve it. So now you can see when I applied the global contact, see how the structure behaves due to this. Since I am telling it to move, but at the same time I have applied the global bonded contact. So it is behaving like it is glued together, but still due to our boundary condition, it is trying to move ahead. So if I animate this, this is not the actual behavior you should follow. This is only for the purpose of understanding that how the two contacts are defined, or how the two contacts affect the behavior. So you can see the bottom of these two blocks. They are unable to move forward. They are stuck at this particular phase. But now what I'll do is I'll apply a no penetration contact between this block, and I'll keep the bonded contact. So observe the behavior after that. So global bonded contact is there. Global means it will be applied to all the parts involved in the assembly. Once I click on contact set and select no penetration from here, there are different contacts. I'll explain you when we are doing the exercise. So select other. I've selected the bottom face of this block and selected the top face of this block. These two faces I need to define. I'm telling that surface to surface contact is there, and don't apply the friction. So the surface is frictionless. Click OK. Now when I run it, okay. So earlier you observed that it was trying to stop it from moving forward, but when I applied the no penetration contact, now this part can move easily. But since the global bonded contact is defined and we have not defined the contact between these two components, it is unable to move forward. Can you see here? The bottom of this, it is stuck. Only the top is trying to move forward. That is why we are seeing this type of behavior. There's a buckling or bending at this very interface. But since we have defined the no penetration contact between these two, it is easily moving to and fro. Since the animation is repeating, that is why it is seen like that. Otherwise, you would have seen only the forward movement. I would have stopped that. So, understood the difference between these
Yes,
two
sir.
things?
Yes. Yes, sir.
Okay. Okay. So now we'll move to that. Okay. So now after this, I need to apply the material. So let's say I'll apply different material for different components now. For the pins that are connecting the yoke at two yokes, I'll consider alloy steel. Since I want it to be stronger, and alloy steel has a yield strength of almost 620. Then to all the brackets, I'll apply to AISI 1020. That is the plain carbon steel. Mild steel. And the yokes, I can define the okay. The base plate also I'll define the AISI 1020. You can write this down, or you can apply the materials of your choice. It's up to you. For the yoke and the spider, we will be considering cast alloy steel. Our bolts are already converted into the connectors, and they are here. So we need not define any kind of material to them. It will consider the by default alloy steel to all the components. Then component contact. So globally it has considered the bonded contact. So whatever the components are in this assembly now, those are glued together. So whatever the results we may get, the assembly will behave in much stiffer way. But we don't want that. So I'll define new contacts here. And since there are number of no penetration contacts, so yeah, as you can see, this yoke will rotate with respect to this. This will be the pin point for this yoke. Again, when we are applying the load to this will try to rotate in the wide this plane, which will additionally rotate this yoke. Since it is connected with the pins and the this spider, it will try to rotate this, and again this will incorporate the motion to the downward direction. So we need to consider all these motions. So obviously there is going to be no penetration contact between them, since they are not stuck together but are moving relative to each other. So for that, I'll define a contact set. You can individually pick each and every component which is touching each other, or you can select automatically find contact sets. So since there are a number of contacts involved here, I'll be selecting automatically contact sets. So in the components, you need to select the top level assembly. So it will consider that in this assembly, whatever the components are in contact with each other, I'll define the no penetration contact for all those things. So I'll say find contact sets. So it has created these many of contacts during the operation. I'll say contact type as no penetration. And let's keep the frictionless for now. Yes, this one thing I wanted to explain to you. Okay. Okay, we will cover it in the next thing. Then in the advanced, since I can see that all are going to have surface to surface contact from the visual inspection, I'll select surface to surface here. Now you need to select all contacts here. Tell them to add. So you go on this. So now all the contacts have been defined. Yes. Now you can see we have created the contact set folder here, and all the contact sets that were found out which are having surface to surface contact with each other, those are present here. So even though this was the part where the nut was fixed, so since we have created the nut connector, it has considered the contact between the nut and the surface as no penetration. Also, you need to remember that whenever you are using the connectors, you need to define no penetration contact between the two interfaces. So like we are using the connectors in this area and this. So this is one of the connectors that is defined. I'll show you how it looks like when we on it. So this is how your bolt connector, countersunk bolt connector look like. So there's no point in defining bonded contact between these two components, as these two components are connected to each other with the help of nuts. So whatever the movement or force transfer is going to happen, that will be through these nuts only. So there is no point in defining bonded contact between them. It should always be no penetration contact whenever you are defining the contact connectors between two components. Okay. So this was about the contacts. Then we need to define one more connection here. So I have removed the pin in this area, so I need to define additional pin. Go to pin connector. Now select the cylindrical faces. So I'll select this and this. These two faces are selected. So the string will be created in this area. Now the next thing is to define the values. So there are two options available with retaining ring. So whenever this will rotate, I want my pin to move in this slot also. So in order to avoid the further wear and tear of the pin, I want it to move slightly in this slot. So I'll say, sorry, there is going to be translation movement. So I have unchecked this. Also, since I am applying the lever load from this to here, it is going to rotate. So also consider that. So with key, I am not considering any key. Then we can define the axial and torsional stiffness. If I consider this rigid or distributed. So if rigid, the interaction between the two components will be very stiff. If I consider distributed, there might be a slight deformation that we can allow it to happen. So there are two values you can find out: axial stiffness and torsional stiffness. So you can find out these values with the help of formulas and write them down. So K axial equal to E times A divided by L. And the unit is Newton per meter. K rotational equal to G times J divided by L. So you can find the value of K axial and K translated from this formula, where E is Young's modulus, A is cross-sectional area of the pin, L is the length of the pin, again G is the modulus of rigidity, J is the polar moment of inertia of the pin, obviously, and L is the length, and its unit is Newton meter per radians. So if you want, you can note these things down in your notebook. I have already calculated the values of the spring. You'll get these properties from the material library at your end. If you want to try it with different material, you need to apply the axial and rotational properties of that material. Okay, I'll keep it as it is. Now the axial stiffness value is, or you can directly include the values that I am entering: 4.3159 e raised to minus 9 Newton per meter, or 18.403 Newton meter per radian. So this will be data for the pins. Now, since these two faces are not touching each other, they may have some movement occurring between them, and we need to incorporate that. But there is a possibility that this face may come so down that it will come in contact with this face, and it will damage or the bracket, or it may result in wrong results. So we need to make sure that these are not intersecting each other while performing the analysis. So to do that, I'll define one more contact set here. At this time, consider this and this, and create node to surface. Since I have selected the edge here, I am not considering the surface to surface contact. This is just to show you how to when to select node to surface. So now anyhow, it won't, these two components won't interfere each other while performing analysis. Okay, yes, one more thing. Definition. So if you see here, there's a concept of gap. So if I want to maintain the gap between these two faces, I can consider that always ignore clearance. So whatever the clearance is there, it will be ignored, and the gap will be maintained always. But if I select ignore clearance, so if I am expecting that this is, let's say, what is the distance between these two? So it's 3.46 mm. So if during the movement of these two yokes, if this yoke comes down a bit, let's say by 1 mm or 1.5 mm, at that time I want to incorporate that in my analysis. So I'll say that let it allow to move up to 1.5 mm in the downward direction, but not beyond that. So to do that, simply go to the contact that I have defined. Let's say I'll say that always ignore clearance. So whatever the gap is there, keep that gap always. If I uncheck this, if I don't consider the gap, what will happen, that there's a possibility that this yoke may directly come in contact with this. So I'm telling the software that maintain this gap between these two components. If I select this option, so and select 1.5 mm, sorry, 1.5 mm. So if the difference between these two is up to 1.5 mm, then it will allow it to move. Beyond that, it won't be able to move. So we will consider that no gap between whatever the by default gap is there, we maintain that. Sorry, no need to maintain any gap since we have unchecked it. If it tries to move downwards, let it be. Okay. So the next thing is we have defined the first we have defined the material properties, then we have defined the contacts. The next thing is to define the fixtures. So from the data, this bracket is not fixed anywhere. So what happens, instead of fixing this, it is grounded on the wall and it is fixed on the wall. So instead, to incorporate that condition, I'll be using the concept of foundation boards here. So to the context to define board, foundation boards. Now select this edge. So it has selected the two edges. Now it is telling me on what plane are you defining it. So I'll select the plane on which the foundation board is there. So this is the plane, and I'll be keeping the default properties. I won't be considering anything else. I'll click on OK now. So it is telling me that on this particular plane that I have defined, there's one more location where we can incorporate the board. Since these holes are created with the help of hole wizard, this message will be visible. If you simply cut extrude the hole, this message won't be available here. So that is one more advantage of the hole wizard here. Okay, so it is only consider the one edge. Okay, we'll try to define one edge only. That is why it is showing me some error. So unselect this edge. So now it has created the two foundation boards, and for two foundation boards we have created just now. This one was showing some error, so we can delete this. These are the two foundation boards, so no need to define additional fixtures. So foundation board, the purpose is that it is fixed in the ground itself, so no need to define any kind of additional fixtures. But we need to define where this bracket is rested. So there's one more contact you can define. Go to contact set, and there's a concept of virtual wall. So if I define virtual wall here, and I need to define on what face. This is basically virtual wall, as the name suggests. I am defining a imaginary wall, which will tell the software that it is placed on some wall of certain rigidity. So I can apply the rigid, consider it as rigid, or I can make it flexible. So if I make it flexible, I need to define the stiffness parameter. So I'll consider it as rigid. I can also define the friction coefficient between this bracket and the wall surface. So accordingly, it will plot the stress values. Okay. So now I think we are done with the setup. The next thing is to define mesh. Yeah, I forgot to mention these things to you. So there's a standard mesh, there's a curvature based mesh, and blended curvature based mesh. So whenever my body that I'm considering, if it does not have any kinds of fillets in it and only sharp corners are there, I can go with the standard mesh. If small fillets are present, so in this particular case, there are small fillets present in this bracket and this bracket. So I need to mesh them as they are necessary for my analysis. I'll be consider also this small. There's a small fillet here also. So I'll be considering it with the curvature based mesh, and I'll keep it as default, or I'll first move to the force mesh. Then minimum number of elements in a circle. So in case of FEA, okay, we'll go one by one. This is the maximum element size of the tetrahedral element it will create. This is the minimum size. then if there is a circle or there is a curvature involved in the model, around that curvature, how many number of elements that I want that should be minimum, that should be followed. So I'm telling that minimum 8 number of elements should be there along any circle. So if I want to capture any curvature in this model, please make sure that at least 8 elements are present there. Okay, along the circumference of that circle. Then there's a element size, growth size. So if let's say if on this circle the element size is coming as 1 mm, I'm keeping the growth size is 1.4. So the next element layer that will be created, it will be of 1.4 size. So since it is 23, so first for the course where it is coming as 23, the first layer will be created of 23 or minimum maybe 4.7, and the elements will grow according to this growth ratio. So next element size will be 4.72 into 1.4, also 23.63 into 1.4. If I decrease this, so element size will be changed accordingly. I'll click OK. So this has created the curvature based mesh. One thing we are missing is to apply the load. So this is the first time we will be introducing the concept of remote load. So I have removed the lever from this just to make sure that the lever would have taken more meshing time. So in order to reduce that meshing time or meshing in that particular area, I'll be considering apply the concept of remote load here. So I'll be selecting these faces where I want to apply the load. We have defined a coordinate system in this geometry itself. The coordinate system. Okay. I'll say user defined coordinate system I want to follow. Now from that coordinate system, where our lever handle end is based with respect to this coordinate system. So we have written few values in the beginning of the lesson for x, y, and z. So I'll define the location of the load from that. So for x, it was 57.15, y, it's 24.6, and z, it's 0. So as soon as I click, now I need to define the force that we are going to apply. So in z direction, I'll be applying a 2.5 newtons of force. Now you can see the lever force direction, but I want it in the reverse. So I'll simply reverse it. So now we have created the remote load, that is to imitate the rotational motion incorporated on this particular shank with the help of lever. So we can do that with the help of remote load. So no need to consider the lever for this particular operation. So by doing this, we are reducing, or we are completely skipping the meshing of that lever part, which is of not much importance to us. So we can simply check what kind of motion that we want to capture. Also, if I want this lever to be deformed while applying the load, it will be considered distributed. If I want this to be rigid, I'll consider rigid. So okay. Now the next thing is to run. So it is telling me that there are certain contact sets that it is not able to function, and those will be emitted from the analysis. So I'll say okay. Either you can stop the analysis and okay, source surface not defined at bolt corrector foundation board. Okay, it is telling me that there is some problem with this. Some foundation bolt. This seems okay. We'll try to redefine those. Maybe I'm missing something. Even though you are defining the connections from the connections, those will be, if they are foundation bolt, those will be stored in the fixtures. Just keep in mind this thing. Define the plane. So one thing you need to follow is whenever you are doing any step, you need to mesh, you need to save the model. So just follow this simple procedure. Now the next thing is to run it. Okay, so curvature based mesh, final mesh size. Okay, so it is telling me that that particular foundation bolt that we have defined, the mesh around that is not properly defined. So you need to do a finer mesh around that area. Since we have considered the coarse mesh, it is not capturing that properly. So create a mesh. We will try to. So we have reduced the element size. I hope this will solve the issue. Surface not defined for bolt connector. Okay. What kind of surface? Okay, the issue might be that there are certain components, since no two components are totally fixed together in a case, there's no point in defining this. Just check it. Okay, if we suppress this and let's try to solve this again. Again, it is still okay. Okay, we'll try one thing here. So we'll try to increase the nut diameter, let's say 13.5. Keep this as 9 mm. And diameter, what is the hole size here? Okay, that is why it was not getting the, we were defining the shank diameter as 8 mm, the actual hole size is 9 mm. That is why it was showing us the error. Let's say what else we can do here. The strength data. Okay, we'll keep each and everything as it is. Let's try to solve it now. Maybe it will be solved this time. Okay, so it is solving now. It is telling me that preload in at least one bolt connector is 0. We want to continue. Since we have not incorporated any bolt preload in the bolts, we are telling that yes, go on. So whenever we are using the bolt connector, it will tell us that you should apply certain preload, as it is the actual practice to be followed. But for this particular analysis, we won't be doing that. So it will take some time to solve, since we have applied the fine mesh and the degrees of freedom are like 291 or 921. So we can take a tea break for like 10 minutes and come back again, and then maybe if it is solved, we can see the results. If it is okay with everyone, we can take the break. If not, you can try it at your end before going, and we can discuss the problem that you are facing at the very moment. So simply type in chat what you want to do. You want to go for a break, or shall we, you want to solve it at your end right now? Hello? Hello?
Yes, sir.
Yes, yes. So I was asking whether you want to go for a break right now, or you want to solve it at your end, and we can, yes?
How long will the session continue today?
Okay, after this, I was planning around 5, but since we have started late, I need to cover the agenda for today. So since there's one more analysis in which we will be considering the beams, solids, and shells in single analysis. So that is the last thing after this. So I think it may take almost 1 hour, 1 more hour to complete.
Sir, actually, this app is taking consuming much data, and also we have to attend some other classes in the evening.
Okay, at what time is your class?
I think around 6.
Okay, then we can do one thing is stop after this, after seeing the results. Then tomorrow I'll from 9:30 tomorrow I'll consider I'll cover the remaining part of this.
Okay.
So tomorrow we'll be actually seeing some advanced topics related to it. So till 5 today we will see the results related to this, and then pack up for today. Is it okay with everyone? If
Okay, sir.
this is till the time it solves, if you have any doubts, please ask me. I'll, in the meantime, I can solve your doubts also related to today's session.
So actually, I have one doubt. That is, during making before the simulation, while we made the assembly of this joint, at that time we already inserted bolts and nuts in these holes, right? But how to remove them after in simulation and add these connectors?
Okay, okay.
I know how
So
to add this connectors. You have demonstrated that, but how
yes,
to remove that I didn't follow.
okay, okay. I'll show you. So currently it is solving, so we won't be able to make any changes. I'll open another. Let's say, okay, we'll consider this geometry only. So you understood how to add the connectors, but if you want to remove any body, how you can do so, whether it may be some bolt connector involved or some washer or some
Yes,
okay,
yes.
okay. So it's very simple. I'll show you. So if you go to the parts, you have all the bodies listed here, right? Simply click on any body that you don't want to consider, right click on it and select exclude from analysis from here. So during that, after selecting this, it will be removed from your analysis and you can remesh and rerun your study. If you want to again include it in analysis, simply right click on that body, simply say include in analysis, it will come back. Now one more thing is that the solver understands that we have made certain changes to it and we have considered that particular body again in the analysis. So but it has shown that it is there's some warning related to the results. So to do that, to regain the results, since we have not made any geometrical changes in the body in terms of dimensions or shape, we can regain our results from properties. Go to there's an option called result folder and there's a refresh button here. So if you click it, if whatever the results were there, they will again appear. So the warning is gone now. Okay.
Okay, sir. There is another doubt that how to do auto convert toolbox fasteners.
I mean, while importing into SolidWorks simulation, that is what you are asking.
Yes, sir. Yes, sir. Yes, sir.
Okay.
Yes.
So while importing into, let's say, now in this geometry there are no fasteners. Whenever you are creating new study, if you are having fasteners from the toolbox, SolidWorks toolbox, it will show you one more option here. It will tell you to directly convert them into the connectors. So once that study is done, I'll show you again. It will take some time to solve.
Okay, sir. Okay, I got it actually.
Okay. So there's an option while creating the new study whether you want to directly convert the fasteners to the connectors, SolidWorks connectors.
Okay, sir.
Is there any doubt? Anyone?
Sir, is it always recommended to use fine mesh? Means
Not always. It depends on the. It actually depends on how much geometry is captured. But fine mesh will give you better results as compared to the default or the coarse mesh, as it captures the geometry more accurately as compared to the two meshes. That is
yes,
coarse
sir.
or the default.
Therefore, in every models or every assembly, we can easily use that fine mesh. Then it will
Yes, yes, but
capture better.
yes, that will be always beneficial at your end also, as it will save the headache of solving the mesh errors. So if you are having strong computational power at your end, at your disposal, and then obviously you can go for the fine mesh. But as you can see, the more finer you mesh the model, the more time it will take to solve.
Yes, sir. Yes, that is a problem.
So you guys are having the SolidWorks on your personal laptop, or is it in the call institute itself?
It is in our personal laptop, sir.
Okay. I mean, you can solve this example at your end. That is what I'm asking. Even after the class. Okay. Actually, tomorrow we will be covering some advanced topic related to this. So I'll brief you related to some more advanced analysis like thermal is there, frequency analysis is there, and nonlinear static, and also I'll take the motion analysis, that is the kinematic related part, tomorrow itself. So I think since today one topic is remaining for today, we will start at 9:30 and maybe end around 2:30 or 3:30 tomorrow.
Okay, sir, no problem. So will it be possible to conduct this class in Google Meet tomorrow?
Actually, in our organization, Google Meet, the recording option is not there. So I can take the class in Google Meet, but the recording won't be available. We have the recording option in the GoToMeeting and Zoom call, but the Zoom call is engaged today and tomorrow for another training. So that is why we have only the option of GoToMeeting right now.
So there is actually another problem.
Yes, please.
That is the license of the SolidWorks will expire tomorrow. Means it was allotted for 1 month, 30 days. So the license will expire tomorrow. Means after tomorrow, we either need to renew the license or to download it once again.
Yes. Is there a time limit for tomorrow, or tomorrow whole day you will be able to access it?
That I can't. That I don't know, because it was written there 1 day left. It was showing there.
Okay, I'll just confirm with someone from the company and get back to you on this. I was told that you are having 1 day left, but let's just I'll confirm it with someone. What exactly is the scenario with that?
If it ends tomorrow, then can we get a new license for the means?
I'm not sure about it, because licensing part someone else looks after it. Maybe Sudeep sir or Suvan sir will get back to you related to this.
And students,
yes.
We are already aware about that. We are arranging something. Please wait for some time. We will update.
Yes.
Okay, sir. No problem. Sir.
So I think it will take some time to solve. Instead, if you guys are okay with it, can we see the completed results of this particular study?
Yes, sir.
If it's not a problem with you, as it will take due to the fine mesh, it will take some time to solve.
Yes, sir.
Okay.
Okay, sir. No problem.
Okay, so I'll pause this in the meantime. And so the file that I have shared with you, there's one more folder in it saying the completed file. You can also refer to it if you have a doubt related to the steps, missing steps, and refer it anytime you want. Yeah, one more thing, like yes. So whenever we are solving the SolidWorks simulation file, this one file is created, that is a .cwr. So all your result data is stored in this file only. So comparatively, you can see the size of this file is also larger as compared to the other file. So if you misplace this file, your result should be gone completely. So make sure that you are storing this file properly, as all the result data will be stored in this. If this file is not there, that means the results are gone. Okay, the results are not there, I think. Let's just sorry. Okay, so this is what the result that I'm getting here. The value is going about 36 MPa. Simply change this. This is what the stress plot looks like. Most of the plot is blue. That means the stress value is very less, but only the stress is developing near this bolt locations. So if I want to know where the maximum and minimum stresses are coming, I can plot them as also. Simply right click on any of the plot, go to chart options, go to show max annotation. So it will highlight the maximum stress area in your model. So this is the area where we are getting the maximum 36.89 MPa of stress. So this may be due to the bolt connectors that we have used. The connectors during the operation, this is trying to move, but the bolt connectors are restricting and imparting the stress on this particular edge or countersunk location. So if you want to see the displacement related to this, you can see the displacement is quite small, 0.005 mm. It is, let's make it more readable. So the displacement value is 0.0051, which is quite small, and it is coming near this particular area. And if I animate this, so we have applied the load on this particular lever, but it is not rotating. So can anyone of you tell me why it is not rotating at this moment? If you could unmute yourself and answer it. It is expected to, since we have applied the remote load here, I'll show that. It is expected to rotate, but it is not rotating at this very moment. So any reason that you can explain this phenomena with?
Unless we apply any twisting movement, it won't move.
It's not like that actually. Anyone
Sir,
else?
Is it fixed to the bracket?
No. There's a no penetration contact between them, so it is allowed to move. It is not fixed.
Is it that we didn't apply motion study in?
No. No. It is related to the assumption that we saw in case of linear static analysis. Can you recall those, the things that we learned in the first half? Even though I am applying the leverage at this moment, I am applying a 2.5 newtons of load. Even though that the load is not enough to rotate it. So I'll tell you the basic assumptions of linear static analysis. There are 3 assumptions that we saw. So I'll move to that slide now. So the response is proportional to applied loads. Material is linearly elastic, and this is the assumption that we saw. The loads are static in nature. That is, loads are applied slowly. So the condition that we are solving, we are considering that the load is not, whenever we are considering the leverage load, there is some aspect that it will try to rotate it. The involvement of time or involvement of rotations per minute will be there. So this particular type of analysis will fall under the dynamic or transient analysis, which will be dependent on the time. So the force variation will be with respect to time, and the direction of force will change according to the change in the direction of rotation. Just a second. Okay. So in this particular, since we are only solving this linear static analysis, the load direction will be constant. Also, the load is considered to be stationary, so it won't allow it to rotate in this particular plane, since we are applying the stationary load. If I was to solve it for the like nonlinear or linear nonlinear dynamic or some linear dynamic analysis where we can incorporate the functions of time. So at that time, I can incorporate the force will be a variation of time. So whatever the rotations per minute that needs to be considered, I can incorporate that in those particular analysis. At that time, we could see the deformations or the rotation that is happening in this analysis. Okay. So depending on your output, you need to select the analysis accordingly. Since we are just in the beginning phase of it, the beginning phase of exploration of analysis simulation, we will be considering the static analysis. But as we move ahead, or as you guys explore more about it, there are some advanced analysis that are involved here. And tomorrow I'll explain you what exactly is non-linear static analysis. So the base, in case of static analysis, the load will be applied in the single step. In case of nonlinear analysis, so suppose this particular example, if I wanted to rotate that, this load will be in this direction. After certain step, this load will change its direction as I want it to be perpendicular to this. So if I want it to move, if this moves, the load direction has to change, and that comes under the nonlinear static part. for nonlinear analysis. So when the load will be applied in the number of steps, I'll explain you these things tomorrow in detail while we start the nonlinear analysis. This is just an introduction to it, that why it won't move. So you may come across this problem that why it isn't moving or rotating. So this might be the particularly reason for that. Okay. So the basic analysis, whenever we are dealing with the assemblies, if the assemblies are having different types of motions involved in it, we perform those motions in case of motion study. So suppose you are dealing with in a piston cylinder assembly. So the oscillatory motion of the piston due to the crank rotation, that can be captured in the motion analysis, but in order to import those boundary conditions into it, you cannot consider all the boundary conditions of an assembly. You need to import the different parts separately into the analysis. So motion analysis will give you an idea about the motion, or if during the motion of the particular component, whether the parts are touching each other, or those parts are interfering with each other, or what kind of reaction forces those parts are developing. That motion analysis will give you the idea about, but simulation will give you the idea about stresses and deformations that are occurring in your assembly or in your part. So this is the difference between the two. Tomorrow when we'll see motion analysis, you will get the idea in better way. Okay. If you guys have any doubts, please ask. Hello.